Okay, we're going to talk about orbital hybridization, orbital shape, molecular shape, and sigma and pi bonds. Now, as you remember from Intro Chem, there are a lot of different types of orbitals, and in organic chemistry we typically deal most often with the s orbital, which we remember is a spherical shape, and the p orbital. Now, p orbitals, there are three of them. We think of this as the px orbital. We can have a py orbital that's perpendicular to it, and a third pz orbital, which is perpendicular also to the other two. Now, these shapes just describe the probability of where an electron might be located. And if we remember, each of these orbitals can hold 2 electrons. Okay. Now, what we find in molecules is that atoms can combine different orbitals to form hybrid orbitals. And these hybrid orbitals are involved in bonding between different atoms in a molecule. And so what we're going to do is try to imagine the different combinations of these orbitals, what type of hybrid orbital they would make, and what are the characteristics of that. And so the first thing to think about when trying to figure out how many orbitals you need is to look at the central atom of a molecule and try to figure out how many electron domains are around the central atom of the molecule. And we'll do some practice in a minute to try to figure that out. Now, for any molecule where 2 atoms are bound together, there's going to be at least 2 electron domains around that atom. If you have 2 electron domains, then you need 2 orbitals in which to house them. And so we will use an s orbital plus a p orbital, join them together to form what we call an sp hybrid orbital, and the shape of that sp hybrid orbital is linear, pretty simple. Now, we've used the s and the p orbital to make the sp hybrid orbital, but there's a couple other p orbitals that aren't involved in this, and so we're going to represent those as extra orbitals here. They'll come into play in some of the molecules we look at. But the sp hybrid orbital is a linear orbital. We have our py and our pz sort of hanging out, not involved in the hybrid orbital. Okay, now if we have 3 electron domains, we're going to need an s and 2 p orbitals to give us an sp2 hybrid orbital. And the shape of the sp2 hybrid orbital is trigonal planar, a triangle and a plane. Again, since we have only used an s and 2 p's, there's an extra p orbital sort of hanging around, and we're going to indicate that as the extra p orbital. Okay. If we have 4 electron domains, this is very common in organic molecules, then we're going to form an sp3 hybrid orbital, and the shape of the sp3 hybrid orbital is tetrahedral. So if you notice, each electron domain around a central atom is going to require the use of 1 orbital. So if we have 2 electron domains, we're going to take 2 orbitals, hybridize them together to form an sp. 3 gives us sp2, 4, sp3. Okay, and we can't forget with the sp and the sp2 that we have extra p orbitals that are unused in the hybrid orbital and may be used for other things. Okay, now let's try to think about this hybridization in terms of a molecule and to see if we can learn anything about the shape of that molecule, or how the electrons are arranged. So let's make a little chart here. Let's have a molecule, and let's start with a simple one. Here's the Lewis dot structure for water. We're going to try to figure out the hybridization of the central atom in water and the molecular shape of water. So here's the central atom, oxygen. How many separate electron domains are there? Well, there's this bond, has 2 electrons in it. This one over here, which is distinct, a lone pair here and a lone pair there. That's 4 places where we have electrons, 4 electron domains. And so how many electron domains? 4. The hybridization, therefore, for this would be sp3. The orbital shape, and again we should probably call this hybrid orbital shape, would then be a tetrahedral. And if we were to draw it, we might imagine here's the central atom, one of our hydrogens here, the other hydrogen there, and the other 2 locations on our tetrahedral are taken up by lone pairs. Now, if we describe water as having a molecular shape of tetrahedral, that wouldn't be quite correct, right? The electron domains are arranged in a tetrahedral pattern, but when we think of the molecular shape, we're really just talking about the atoms that make up the molecule. So if we just look at how the atoms are arranged in water, we would say that water is bent, right? And again, the tetrahedral geometry has bond angles of around 109.5 degrees. The lone pairs tend to repel a little more strongly, so we might imagine that this bond angle here would be less than 109.5 degrees. Okay, now let's take another molecule. In this case, we're going to take a simple organic molecule, ethylene, which has a double bond in it. Here we have 2 central atoms, but they're very similar to each other, so let's just think of one at a time. Let's look at this carbon. Now if we count the electron domains around it, 1, 2, and then we have this double bond. Now this double bond has to exist between these 2 carbons in order to bind them together, and so in terms of domains, this counts as 1 location or 1 domain. So really we only have a total of 3 electron domains around this carbon, which house 8 electrons. So 3 electron domains, since the double bond counts as 1 domain. The hybridization, sp2. The hybrid orbital shape would be trigonal planar. And if we're to try to draw this molecule, we can imagine here's our central carbon with a trigonal plane of hybrid orbitals around it. Here's our hydrogen up top that has its s orbital. Another hydrogen down here has its s orbital. The other carbon in this molecule would also have a trigonal planar with its hydrogens on the other side. And what we see are the formation of these bonds. Okay, a hydrogen bonding with this carbon through direct overlap of orbitals. We call that direct overlap of orbitals a sigma bond. So we have a nice overlap here that gives us 1 sigma bond, another overlap here, another sigma bond, sigma bond, sigma bond. We can see in between these 2 carbons, we also have a direct overlap of the sp2 hybrid orbitals, which gives us a 5th sigma bond. Now that only is describing 5 bonds, and if we look at this molecule, there's actually 6 bonds there. This double bond is 2 bonds. So where's that double bond come from? Well, if you remember, when we looked at sp2 orbitals, hybrid orbitals, we said that there's this extra p orbital that's unused, and so we have to consider that when we think about molecules with double bonds and triple bonds. And this is where we get indirect sharing of electrons through this p orbital, and we call that type of bond a pi bond. So if we look at ethylene, we can see that through the hybrid orbitals between the central carbons and the s orbitals of the hydrogens, we have direct overlap, or sigma bonds. We also have a sigma bond between the two carbons, between their sp2 orbitals, and then this extra p orbital allows for a pi bond to occur. So in ethylene, we would say that there are 5 sigma bonds, 1 pi bond. The molecular shape of ethylene is trigonoplanar, or actually the molecule is planar in shape. There's no really three-dimensional geometry to it. It's just one plane in the paper. So we can call this a planar molecule. Okay, let's look at one last molecule. This is the benzoate ion. I'm going to draw out all the carbons here. We have a ring with some double bonds in it. We have a carbon coming off of that ring with a negatively charged oxygen, and each carbon in this ring has one other bond associated with it. Okay. Now, when we think about this molecule, it's a little more complicated. There's lots of central atoms here, but really we can think of looking at each carbon in this ring. Each carbon in this ring has 3 electron domains, 1, 2, and then the double bond counts as 1. The hybridization, sp2, trigonoplanar, and we can think of the shape of this as being a planar ring, right? Each carbon is existing in a trigonal plane, has an extra p orbital that's forming a separate pi bond. If we consider this carbon, we also see that it has 1, 2, 3 electron domains. It's also trigonoplanar, and it's forming sp2 hybrid orbital, plus it has its extra p orbital, which is able to interact with the oxygen to form that double bond. Okay. So even though this is a pretty complicated molecule, overall the molecular shape of this is also planar, just like ethylene. It's formed from a bunch of sp2 trigonoplanar hybrid orbitals. Overall, this is a flat planar molecule. If we were to count the number of sigma bonds and the number of pi bonds, it's pretty straightforward. For each carbon here, we've got 1, 2, 3 sigma bonds and 1 pi bond. On this carbon out here, we have 1, 2, 3 sigma bonds and 1 pi bond. So let's figure this out. We've got 1, 2, 3, 4, 5, 6 bonds holding the carbons together, plus 6 bonds, sigma bonds with their substituents, plus 3 pi bonds. So we have 12 sigma bonds within this ring, plus 1 here, 13, 14 sigma bonds, and our 1, 2, 3, 4 pi bonds. Pretty much every single bond is a sigma bond. Every double bond is a sigma plus a pi. If I had a triple bond is a sigma and 2 pi.